Hi, welcome back to INST 314, Statistics for Information Science, with your host, Shawn Janzen. And we're going to continue our talk on one-sample Z and T hypothesis testing, but we're going to carry it from before where we were talking about means to now talk about proportions and how we can do tests with proportions. So let's go ahead and learn how to conduct one-sample proportion tests. Now, some of these things we're going to carry over the same understandings. We're going to use the same rules that we've applied for how we write hypotheses, how we choose alpha, how we look at critical regions. This is all the same. We're still starting with the basis of a null hypothesis, and in this case, we're talking about that there's no proportional difference between your sample and your population, and that all Z distributions still rely on some level of standard deviation and sample size. But this does allow us to use the idea of consideration for nominal variables, because nominal variables can have proportions between them. So let's go ahead and remember the central limit theorem's conditions on how they apply to proportions. Now we have to assume that it's random and independent sample. That's going to matter no matter what kind of statistical test we're doing. We also look to see that the sample is less than 10% of the population. That's the same from our previous version with the means. But we differ again when we come to how we define what is a large sample. And a large sample we're talking about in terms of successes and failures, where successes is sample size times the probability, should be greater than 10, and failures are n times 1 minus the probability of interest, and that should also be greater than 10. We're not looking to define if successes and failures mean that it's actual success, actual failure, right, wrong, better, worse. It just means that you have some sort of binary outcome, and that one of them is your area of interest, and that's the one you call success, and the other one that's not as much of an area of interest is the failure. Now, when you have these met, then the central limit theorem for proportion says that we are going to have a normal distribution of these proportional probabilities based on p hat, which is our sample proportion that's going to estimate the population proportion at a given standard deviation equal to the square root of p times 1 minus p over n. This all comes from the central limit theorem discussion we had before, so I'm not going to spend too much time on this now. Now, the math on how we get the z-score here is going to be a bit different than what we're used to seeing. The z-score here, in this case, I'm using p sub s to represent my proportion from the sample. P sub u is my proportion from the population. And I have the difference here. This is the same understanding when we had the means where you had an x bar minus mu. In this case, we have some sample proportion minus the population proportion. So there's still a difference up in the numerator. The denominator is still a measure of standard error. However, how we calculate that standard error is different. In here, we are doing the square root of p sub u times 1 minus p sub u divided by n. And like I said, all of that square rooted, that goes into the denominator and becomes our standard error. Now note, with these proportion tests, all of them are going to be z-scores. There are no t-scores for the proportions testing here, so they're all z. Now let's go ahead and put this into an example problem and see how this works. Let's see if we want to know whether more than 50% of Maryland voters are going to vote yes on a certain proposition at the ballot box. We get a sample of 250 people and find out that 140 of them say that they would vote yes. So let's go ahead and put this into a hypothesis test. We're going to go ahead and run it through our procedures here, formulate our hypotheses, do our preparation, check the z-score using the formula for the proportions, find the p-value, and interpret the results. So the steps for hypotheses here, we're going to say that there's a population proportion equal to 0.5, and that's our null, and our alternative says that there's going to be more than 0.5 for what we're working against here. Now, keep in mind, this 0.5 here just comes from the example. It's not referring to the 0.5 that I had in the previous lecture slides when we were talking about the confidence intervals. In that case, we used 0.5 because we didn't know the population proportion. And in this case, we're going to go ahead and use an estimate for it. So now let's go ahead and work on setting the conditions for doing this one sample test. Our alpha is at 0.05, and we're going to assume that our sample is random and independent for now. We can worry later on other video discussions if it actually is or isn't, but for the purposes of the discussion, we're going to say that it is. We have to figure out, is our sample large enough? So this is where we're looking for the greater than 10 for successes and failures. To get the yes votes, we're taking our 250 multiplied by our estimate proportion of 0.5, and that tells us 125. We're good on the success, and the no's are 250 multiplied times 1 minus 0.5, which also gives us 125, so we're good on the failures. We're good that way. And then is our sample less than 10% of the population? Well, our population is all of Maryland's voters, and so 250 is definitely less than the population of Maryland. When we go ahead and let's calculate the z-statistic for this. So we get our z-score formula, and up top, our p sub s, this is the proportion from our sample, and we had 141 out of the 250. So the proportion for that is 0.564, and our hypothetical proportion was 0.5, so that's our numerator. And then the denominator, we're setting up our standard error. So p sub u was the 0.5 minus 1 minus p sub u of 0.5 divided by our sample size of 250. We do the math. It comes out to 2.024. What do we conclude? So you have a z-score of 0.242, an alpha of 0.05. What do you think it's going to be? Go ahead and pause the video for a moment. Take your time. I'll wait. All right. So now that we're back, think now that the two-tail alpha, it's going to have a z-score critical value of plus or minus 1.96. And our t-score obtained, 2.02, is larger than our 1.96. This means we are statistically significant and we can reject the null hypothesis. This means that our sample is indeed different from our, well, it says that we are going to go ahead and reject the null hypothesis, that our sample is going to probably be voting yes on this particular proportion, that we are going to exceed that 50% threshold that we were looking at. If we want to go ahead and get a p-value for this, let's turn to r, and we're going to do the p-norm function on our z obtained of 2.024, comma, lower tail equals false, and it's going to give us the probability of 0.0214, and it keeps going. And our p-value of 0.02 is less than our alpha of 0.05, which is going to confirm the result that we had there. So it definitely seems that there is a difference, and that difference is in favor of voting yes on the proposition. Now, let's go ahead and talk about proportion confidence intervals and how the math looks like for this. Now in this case, we're going to use p hat instead of p0 because we're lacking population data when we build these intervals. So we're going to start with p hat as our sample, plus or minus z, times p hat times 1 minus p hat divided by n. And note, you might also see it as p sub s, and so I rewrote the same formula for you as p sub s. Why am I using both of these? Because I know that when you go out into the job market, that if you forget some of this, you might look it up on the internet. And on the internet, you're going to see examples for both, where some people use p sub s and some use p hat. They're used interchangeably, and I want you to become familiar with both in case you happen to see them. Now let's go ahead and use another example here where we're talking about these proportion confidence intervals, and we're going to say that we're going to look at the proportion of students at Hogwarts who run afoul of Professor Snape each year. For those of you who are not familiar with Professor Snape and Hogwarts, this is a Harry Potter example. So say we conduct a survey and find out that 35 out of 80 randomly sampled young witches and wizards got on his bad side that year, and Hogwarts has approximately 280 students across the different years of school. So first let's identify what is the population, what is the population parameter, the sample, and the sample statistic. Go ahead and pause the video. I'll wait while you think about it, and we'll come back. Okay, now, the population are the 280 students at Hogwarts. The population parameter is the total proportion of those who run afoul of Professor Snape. The sample is the 80 students that we've surveyed, and the sample statistic are the 35 over the 80 that run afoul, which is going to give us a probability of 0.4375, or approximately 43.75%. Now, we want to see, does that proportion fall within a 95% confidence interval? So how would we go ahead and build out this 95% confidence interval for the proportion? See if you can calculate it on your own, and while you pause the video, and we'll come back. All right, now that we're back, let's go ahead and use the 95% confidence interval formula here. So I'm going to use the sample proportion I found of the 0.4375 plus or minus 1.96. That is the z-score associated as the critical value at 95%, or alpha is 0.05. And then we're going to take that proportion and plug that into the numerator of that standard error there, 0.4375 times 1 minus 4.375. And that's going to be divided by our sample size of 80. All that's going to be square rooted. And that's going to produce for us an interval of 0.329 to 0.546, or approximately 32.9% to 54.6%. Now note, that interval is pretty large. So what if we wanted to figure out the sample size we need? Because our interval was rather large. So if we need to determine how large of a sample we need to obtain a specific margin of error. So the margin of error for the SNAPE example here was plus or minus 10.08. That's about a almost 11% margin of error on both sides of the average. But what if I wanted to narrow it to a 0.03 or 3%? So a total margin on either side of the proportion of 6%. Well, let's take our margin of error portion and work it backwards. You have the Z-score 1.96, and in here I'm just going to plug in a 50-50 to kind of maximize out what it potentially could be. And if I reverse this formula all around, so n is unknown, and do the math out, we would need almost 1,068 students in order to get a margin that small. But unfortunately, there aren't that many students at Hogwarts, so it may be difficult to get confidence intervals that have small enough margins to get a very refined choice here. And on that, I'm going to go ahead and leave you on this particular video, and I'll see you all next time.